Hello everyone. Have you ever wondered why it's often recommended to standardize or normalize inputs before feeding them into your deep learning model? It's like giving your model a level playing field to work with, which can significantly boost its performance. But what exactly does this normalization mean, and how can we seamlessly integrate it in our deep learning models to enhance their capabilities? Let's look into this important topic today. So, welcome to Data Analytics, where concepts are explained in a simplified manner. We all know that in a typical neural network, information flows from one layer to the next layer, with each layer's output becoming the input for the next layer or the subsequent layer. Now, let's look into an example. We have a neural network which takes three input features. The first feature is number of employees, which is ranging between 1 and 100. The second feature is salary of employees, which is ranging between rupees 10,000 and rupees 3 lakhs. Finally, the third feature is age of employees, ranging between 18 and 65. Now, if we directly feed this input as it is to this neural network, it will be very difficult for the neural network to learn optimum weight values during training while minimizing the loss function. And hence the weights will be drastically different from each other. This will make neural network unstable and it will eventually cause vanishing gradients or exploding gradients problem. To overcome these problems, we need to do normalization of input features as well as implement correct initialization of model weights. But these problems like vanishing gradients and exploding gradients problem may again come while training. The solution to it is batch normalization. So what exactly is this batch normalization? Well, its name gives a hint. It's all about dealing with batches during training. But to simply put it, batch normalization works by standardizing the input of a layer across a single batch of data. Here you all can see that between each layer we have a batch normalization layer which is highlighted in pink color. Now, you all might wonder, couldn't we just calculate the mean and variance at each layer and normalize that way? Now the hitch here is that during training, as our model evolves, the parameters also change, right? Causing the activation in intermediate layers to fluctuate. Calculating mean and standard deviation across the entire training set for each iteration becomes time consuming and somewhat futile as well, given that activations are constantly shifting. That's where normalization comes in to save the day. Now this entire concept of batch normalization was introduced in this paper in 2015. Batch normalization tackles the issue of internal covariate shift. Now this fancy term refers to the problem of the distribution of inputs to each layer changing as training progresses and parameters shift. But hold on. Not everyone agrees on this explanation. Now in this counter paper by Santurkar and team, the authors argue that the batch normalization smoothens the loss function over the parameter space instead. While the inner workings of batch normalization might not always be crystal clear, one thing is undeniable. It consistently, or the batch normalization consistently delivers impressive results across various problems and models. Moreover, batch normalization also comes to the rescue when grappling with vanishing gradient problems, which is a notorious issue in deep learning. In the original ResNet paper, author observed that backward propagated gradients exhibit healthy norms with batch normalization even in plain networks. Now that we have understood the batch normalization, let's actually implement. So this is the entire code for batch normalization. I will provide a link in the description so that you all can access this particular code from my GitHub repository. The first step is we will import all the necessary packages which are needed. So NumPy for numeric operations, we have Matplotlib for plotting graphs, we will be using CIFAR10 dataset. Then we will also import few necessary components from Keras to build and train neural networks like conv2d, maxpool2d, flatten and dense layers. We will also import this two categorical function for one-out encoding. Now after importing all necessary packages, we will load the dataset. So we will be loading this CIFAR10 dataset. Now this particular line, it loads the dataset into four variables, xtrain, xtext, ytrain and ytest. After that we will be pre-processing the data. This particular four line convert these pixel values to floating point numbers and normalizes them between 0 to 1. Earlier they were between 0 to 256 and now we are converting them into 0 to 1. This CIFAR10 dataset has 10 class. So this two categorical function, it converts categorical labels into vectors of binary values. The next step is defining the entire model architecture. We will be using these two convolutional 2D layers, and this particular model, it doesn't have any batch normalization function, as you can observe. So it starts with this convolutional 2D layer with 32 filters, each of size 3x3. The activation used is ReLU, rectified linear unit, and the padding is kept to be same. Then with this convolutional 2D layer is followed with max pooling 2D layer with a pool size of 2x2. Then another convolutional 2D layer comes into picture with 64 filters, followed by another max pooling 2D layer. The output of this is then flattened to get a one-dimensional array. Then there are two fully connected dense layers with 128 number of neurons in first layer and 10 neurons in the final layer, representing the 10 classes of CIFAR dataset. The activation for last is softmax. Now we will be compiling the model. The model is compiled using Adam optimizer, and we will be using categorical cross entropy because we have 10 number of classes. If we had 2 number of classes, then we had used this binary cross entropy. Now accuracy is chosen as a metric to monitor during training. Now let's fit the model, or let's train the model. We will be training the model for 20 epochs for batch size of 128. Okay. Now these are the lines which will plot the training and validation accuracy. Once the model is trained, we can see a graph like this. So this graph is without batch normalization. Now let's write a code for batch normalization. In this, with batch normalization, the entire architecture will remain same. A difference is that we have introduced batch normalization between the two layers of this neural network. So for this batch normalization, we have imported batch normalization function from this keras.layers. So this is important, batch normalization and batch normalization layer between the two layers. Now we will compile the model, we will train the model, and finally we will be plotting the model. Now in order to compare the two graphs, that is this one, the without batch normalization and with batch normalization, I have written another code just for your reference so that we can see them side by side. So you can refer it here. I have defined this model with batch normalization and model without batch normalization in these two variables, and then one by one models will be trained for model in model. So this loop will run for 2 times and 2 models will be trained for 20 epochs each. So first model will get trained, second model will get trained, and finally the comparison will be shown. So here we can see that the model with batch normalization, so this blue line, is converging faster than the model without batch normalization. So that's it guys. So hope you have understood the nitty-gritties of batch normalization. If you have watched this video till now, do like this video, comment on this video for your feedback, and do subscribe your favorite channel, that is DataFuse Analytics. Bye bye guys and take care.